Okay, let's talk about the Lorentz transformations. The laws of physics, for many parts of it, and in special relativity in particular, obey spherical symmetry, which means that essentially you can choose a single space dimension, because in the space xyz time you can rotate that space to the direction in which the movement is occurring. And so we don't really need to have x, y, and z. We could call it r, but we're going to call it x. Now, you can rotate the three-dimensional coordinate systems in any angle you want. And it turns out that the same thing is true in a four-dimensional coordinate system. Minkowski space is a four-dimensional system. So rotating space into time are called by physicists boosts. And we have here the Lorentz transformations. Bob's x prime, or Alice's x prime, doesn't matter which one, is equal to gamma, the same 1 minus beta squared to the 1 over square root of 1 minus beta squared. And so you have x minus vt, and you have ct prime. Again, we're using the conversion factor speed of light to measure time in meters. And so the t prime is gamma times t minus v times x, where gamma is, as I said before, 1 over the square root of 1 minus beta squared. There are the traditional assumptions that I've discussed before. If there are two observers, Alice and Bob, Alice is assumed to be the velocity 0, not moving, and B is assuming to see Alice's clock moving, and hence B is called the moving observer. The invariance of proper time means that the dt squared is equal to minus ct prime squared plus x prime squared, which is equal to ct squared plus x squared. And in a version of the presentation that I'm going to send to you, I'll have an appendix that shows that this invariance in proper time follows the Lorentz transformations. Okay, what do the coordinate systems for different observers look like? Well, Alice is the rest frame, and hence looks very Cartesian. Alice is the black axes x and t, and has the red dashed markers, And Bob's t prime is the blue coordinate system, moving to the right with c over 4, where c is the speed of light. So the direction of Bob in Alice's coordinate system is directly here along the blue line. So this gives you, anytime you want to know where the coordinate system of somebody who's moving relative to somebody else is, just draw the trajectory, and lo and behold, you will have the time axis of Bob. In the other case, the angle along here and here are the same, and so this is the x prime coordinate, or Bob's x prime coordinates. And the red light cones are shown here. Notice the light cones are identical to Bob and Alice's coordinate systems. This is what it means to say that the speed of light is a constant. The light cone is identical for all observers, regardless of their velocity. So this is how, and you can see that Bob's coordinate system is not Euclidean it's got little parallelograms as you measure the things that are going on. Also, the sizes are not identical. This distance and this distance for Bob are not the same as these distances in Alice's coordinate system. So let's take a look at a particular case, and we're going to let Bob be moving to the right by 0.6 times the speed of light. We have two, this is the origin, we have two points that are of interest here. The first is Alice's time at some particular point here. I believe it's 0.8 in the dimensions that we have here. And that is her time, and since she has no moving, she's co-moving, she has no x change, this is her proper time. The other point is the red one, and the red one lies along Bob's co-moving frame. Now this is Bob's co-moving frame relative to Alice's. So here Bob has the same time in Alice's coordinate system, but a different coordinate time in his time system. But for Bob, the red dot is another proper time, although it's not the same time as Alice's proper time, even though they both have the same time. These points can all be calculated using the Lorentz transformations, and you will find proper time the same in both coordinate systems. So let me show you the table of results from doing that. Here we're saying that Alice is not moving relative to Bob. Bob sees Alice's clock as moving. The blue point is Alice's co-moving proper time, and the red point is Bob's co-moving relative time, because that is right on the axis, the time axis of Bob. Okay. Now, when you compute either the position of Alice, X and T in blue, you will get 0 and 0.8. And of course, since there's no positional movement on Alice's part, the proper time is simply 0.8. Bob, on the other hand, has different measurements. Those are given by the Lorentz transformations, and they will show that the X prime point of Alice's blue point is minus 0.6 and T equals 1. Again, as we said, the time of Bob's measurement is longer. This is time dilatation. So Alice measures the blue point at T equals 0.8, but Bob measures the blue point at 1. However, he thinks that Alice's position is minus 0.6. When you compute the proper time, Bob gets the same proper time as Alice, 0.8. What about the red point on Bob's co-moving coordinate system? Bob measures his point to have no position, 0, and he has a time of 0.64. Alice, on the other hand, says that Bob is to the right of her at 0.48, and at the same time as where she was, 0.8, because we saw those were two right angles, and both Bob and Alice measure the proper time as 0.64. Now, because relative to Alice, Bob is moving at velocity 0.6 c, his proper time, the time he actually has going on in his heartbeat or whatever else, is the proper time. And because he's moving, he has a shorter time than Alice has. Alice has 0.8 meters of proper time, whereas Bob has 0.64 meters of proper time. So this difference, the fact that any moving object relative to some other observer will measure the proper times to be exactly the same, but the one moving relative, Bob moving relative to A's clock, his proper time will be shorter. And it is this distinction that is the basis of the twin non-paradox that seems to confuse so many people. So I'm once again going to call a stop here and ask if there's any questions.